also called a synthesis reaction. So combination or synthesis, depending on the book, depending on the professor, we have both of those that are available. There's going to be these rules. You need these, right? This Chem 209, this is your entire second exam. It's this piece of paper, which, by the way, again, you get to use on your quiz for this module and for your exam. So you definitely need this. And if you don't have a printer, then write it out by hand, but you definitely need this. And so you're going to see the first sentence says, most metals react with nonmetals to form ionic compounds. Or a nonmetal may react with a more reactive nonmetal to form a molecular compound. Or a compound and an element might combine to form another compound to form a higher atom-atom ratio. And so all of these you're looking at and you're like, what? What do these mean? So for example, this is what we mean by a higher atom-atom ratio. So if you have, it's like it's very mad at me. So if you have CO2, CO and O2, a higher atom-atom ratio would be CO2. And so we're going to talk more about what these mean as we go. Okay. And this is the literally combination synthesis reactions. It's just the very top piece of the handout. So if you look in your camera right here, you see all I did was copy and paste it here. So we're going to go over this. So I'm going to go and grab a different pen from my computer. So I'll be back in 10 seconds. And then we're going to go over this. I'll be right. Got a new pen. Okay, so now combination synthesis. What we did before is we classified these. So I'm going to go over these rules and then we're going to practice these rules. So I want to remind you, this piece right here, you get to use. So you just need to be able to apply it, right? So the first one, metals react with nonmetals. Remember, here's our metals. Here are nonmetals to form ionic compounds. A nonmetal may react with a more active nonmetal to form a molecular compound. We're going to talk about that one in a little bit more detail. A compound and an element may combine to form another compound if one exists at a higher atom-atom ratio. That was the CO2 one we just saw. Here's another one. A metal plus an oxygen makes a metal oxide. A nonmetal plus oxygen makes a nonmetal oxide. Metal oxide plus water makes a metal hydroxide. There's those polyatomic ions. Here's another one, non-metal oxide. So something here with an O plus water makes an oxy acid. Remember our oxy acids like nitric acid, sulfuric acid, phosphoric acid, all of those oxy acids. And then ammonia, we memorize that one, right? NH3 plus an acid, so we have to remember our acid naming, makes an ammonium salt. Okay, so here are some examples of how this works. So I should really put numbers on here. So a metal plus a nonmetal makes a salt. That's one of our, so here's our metal, here's our nonmetal, and it makes a salt. Remember, a salt is any ionic compound. We just literally call NaCl table salt because it's the one we know most, but any ionic compound is actually a salt. Okay, here's another rule we just looked at. A metal oxide, so calcium is a metal, oxide, oxygen, plus water makes a metal hydroxide. So it's the calcium, and now we have a hydroxide. Another one. Here's another one with two nonmetals. Aluminum and bromine make aluminum bromide. Okay, so now this is the kind of questions you're going to see in this module. And this is your whole exam number 2. And you're going to see why this is very helpful for studying for your exam number 1. So here's the question. Literally, sodium metal reacts with chlorine gas. That's the question. You have to write a balanced chemical equation, right? So you see sodium metal. So that's Na reacts with chlorine to form something. Well, here we are. Here's the rule. So what we do is we look at it. We go, okay, this is a combination reaction. And then we find the rule that matches it. Sodium plus chlorine, so a metal plus a non-metal makes an ionic compound. But we have to remember, I forgot, let me just, BRINCLHOF, Brinkelhoff, right? When chlorine is by itself, it is a diatomic, right? So that's something we have to remember. And then the next thing we have to do is we have to balance it, right? There's 2 chlorines over here, 1 chlorine over here, so we have to put a 2 there. That messes up sodium, a 2 here, and now we're gonna start doing the states. Now, metals are solids, right? So metal, anything to the left of the periodic table is a solid, so we can put an S there. For Brinkelhoff, all of these, except for bromine, are gases at room temperature, right? And then all ionic compounds are also solids. Metals are solids, ionic compounds are solids. These Brinkelhoffs are gases, except for bromine is a liquid. But if you accidentally put bromine as a gas, it's probably okay. So we're going to start working on these states. Okay, here's another one. I can't erase everything now because my computer and Zoom are having such an argument. Aluminum metal reacts with fluorine gas. So we have aluminum metal plus fluorine. And remember, fluorine, when it's all by itself, is part of Brinkelhoff. That means it's a 2. And now we know this is a combination reaction because we have 2 things becoming 1. That's why the classification is so important, because when you classify the reaction, it's going to tell you where to look on the sheet. So you're either going to look at one of these headings depending on how you classify the reaction. So this means they are going to come together. And here is excellent practice for exam number 1. It's not just ALF, right? We have to balance the charges. Aluminum is a +3, fluorine is a -1, so therefore we need ALF3. And then we're going to combine that. Now we have to balance the reaction. 3, 2, 2. Now again, if you can't balance it that fast, you can do that whole entire little like balancing series we talked about. And then we need to think. Remember, all metals are solids. Aluminum is a metal. Brinkelhoffs are gases. All ionic compounds are solids, right? And so this would be the answer to the question. And so the reason that elements and compounds module, or all of your exam 1, was so important is because now we're going to use all of that to write these balanced chemical equations. Okay, so now, and we're going to keep coming back to those. Now let's look at a couple decomposition. So decomposition is just the second piece. So step 1, classify the reaction. You got to classify the reaction or you don't know where to look on the sheet. So it's 1 thing becomes 2. So here's some examples of some decomposition reactions. So metal oxides, which this one is number, I can't remember which one this one is. Oh, it's the second to last one on your sheet. Metal oxides decompose when heated. What does that mean? So here's a metal, lead, oxide is oxygen. Decompose means they split apart, right? And so this is a special one, which we're going to talk about in just a second. And so can anybody find, let's just do this one right now. We'll start something difficult. Which rule would this be on your sheet? Can anybody see this one? I'm going to write it here because I don't have it. So this one is
metal oxide.
Yes, makes
A metal oxide, oxygen, or metal and oxygen.
yes, exactly, with less oxygen, right? Plus oxygen. It's the second one. So this is how you know it's one with one less oxygen plus an oxygen. And again, this is going to take us a little while to figure these out. Another one, metal oxides decompose when heated, or carbonates form with CO2. And so here's a carbonate, here's our CO2, here's our metal oxide, or H2O2 decomposes to form steam. So the question is, how do we know these products? Again, the key to this is using this sheet. So what I've done here, what you're seeing here, these little rules are on your sheet also. This is just presenting it in a different way. So here's a rule, oxides of halides. Remember, what's a halide? Anybody remember? Great practice for your exam.
7? Group
Yeah,
7?
Group 7.
Group 7.
Yeah, group 7. So oxides and halides, so O's in group 7. Metals of Au, PT, and Hg decompose into the elements, right? And so here's chlorine is a halide, decomposes into the elements. The reason these are 2s is because they're Brinkelhoffs, right? Peroxides. So peroxides are O2, 2-. The one we know is hydrogen peroxide. How can you tell if it's a peroxide? Usually we only use hydrogen peroxide. It decomposes into oxides and oxygen gas. So this water happens to be an oxide. All an oxide means is it's an element with an oxygen. That's all oxide means, element with an oxygen. Here's a metal carbonate, metal carbonate. And then here's a rule. And again, we're going to look at these rules, except those of group 1A. So this means not group 1. So not lithium, sodium, anything but those. Decompose into the metal and an oxide. Again, here's our metal. Just means metal with an oxygen and CO2 gas. Now the next one talks about oxoacids. Remember, those are perfect. We just learned those for exam 1. So those oxoacids decompose in a similar way, right? And so usually a water is removed. And so we actually looked at this one on your Chem 101. Usually we have a whole lab with it, so we talk about it much more. This is a hydrate. Right? So a hydrate just means that water is loosely attached. I'm hoping that in our lab kit we have this lab because it's quite a fun lab. And so what it does, this little dot means attached water, and this means 5 waters are attached to it. So we would call it copper sulfate pentahydrate for 5 waters. And so then when we can decompose it, we release the waters. Now here's another one. Ammonium compounds, remember? Ammonium is NH4 plus. Ammonia is NH3. Very important difference in those two. So an ammonium compound, that's NH4 plus. They lose ammonia. Right? Here's our ammonia. Actually, I should probably put this here. So there's that whole ammonia issue. Okay, so I gave you the rule this time. Actually, I didn't. So here we are. Platinum, what is that? Platinum 4 chloride, right? Decomposes into its elements. So looking at our sheet, So you should, when you see this, the first thing you do is go, okay, what kind of reaction is this? Decomposition, right? So we classify the reaction. It's a decomposition reaction. Step 2, find the rule. Can anybody find this rule? And which rule is it? I should really put numbers on this sheet.
Oxides and halides of gold, platinum, and mercury decompose to the elements.
Yep. So that's 1, 2, 3, 4, 5. It's the 5th one on the sheet. So if you're looking at the sheet, it's number 5. And so that's what you do. You classify the reaction, and then you go to the sheet and you go, okay, what happens? And then you find the one that matches it. And so number 5 says oxides and halides of gold, platinum, and mercury decompose into the element. Well, here's platinum. That's a halide. So it decomposes into the elements. So into the elements would be PT and Cl. But that's not the whole story, right? Because now we have to figure out there's something that we need to do with this. What is true about this chlorine?
There's 4 of them.
There are 4 chlorines, but there's something special about this chlorine. Yeah, it's diatomic. Okay, so that brings me to equations. When we're writing or balancing equations, the reason this 4 is here is because it's balancing out the charge of platinum. So this 4 means platinum's charge is +4. That's what this number means. It's the charge of platinum, right? This is good review for our exam. Chloride is a -1 because it's in group 7 and we've memorized it. So when we do our little crisscross, this becomes a 1 and this becomes a 4. So, right, this was a +4, this is a -1. That is why this 4 is here. So the reason we have this 4 is to balance the charge. So we don't bring the 4 over to the other side. So what we wouldn't do is we wouldn't do this, right? The reason this 4 is here is because it's balancing the charge of the PT and the Cl. Remember, because the net charge in the ionic compound has to be 0. So we never, ever, ever bring these subscripts over unless it's a polyatomic ion. And we'll get to those, right? So that means it's kind of like a break. This has nothing to do with this side now, right? We need to do this side, we need to treat it completely separately. So platinum is a metal, so we're good. Cl is a Brinkelhoff, it's a diatomic, so we have to add a Cl2. And now, just like we did last week, now we need to make them the same on both sides. We need to have the same number of PTs. I'll do it like this. And the same number of Cl's on each side. So we have 1 PT here, 1 PT here. 4 Cl's on this side, 2 Cl's on this side. So now we have to make those the same. Remember the law of conservation of mass. So if I multiply this by 2, I put the 2 up here, so that's 4. Now we have a balanced chemical equation. But we can also add the states, remember? All metals are solids. That is a metal, therefore it is solid. Cl is a Brinkelhoff, so therefore it is a gas. So it's adding on to what we just did, and it's 100% using exactly what we learned for our first exam, right? Okay, and there's some steps, and you have to follow the steps. The first step, classify the reaction, right? The second step, find the rule. Third step, write your products. Fourth step, balance your charges. Last step, balance your reactions. Okay, so again, here are those rules that I'm looking at. So I should really put numbers on these, but I forget. Instead of little dots, that would make your lives easier when we're finding these. So these are the rules that I'm talking about and looking at. And again, this is why this piece of paper, without this piece of paper, you're just sort of lost in all of our lectures for this class, for this whole module. Okay, so let's try this one. Mercury 2 oxide is heated. So I told you it's a decomposition reaction. So step one, check. Now we need to figure out what does it make. So we need to find the rule, and happens to be the same rule we just used, of oxides and halides of gold, platinum, and mercury decompose into the elements, right? And so this sheet, by the way, is in the module and in the announcements from last week and this week. So it says reaction handout notes. So it's on Canvas under the module, and it's in the announcements this week and last week if you need to find it. So print that out for sure. Okay, so when we do this, it says that, again, the rule is oxides and halides of gold, platinum, mercury decompose into the elements. Well, step one is a perfect mercury oxide. If this is a +2, this is a -2, so we're good. Decomposes into the elements. Okay, what's wrong with what I have written?
Oxygen's a diatomic.
Oxygen's a diatomic. Remember, they're only diatomic when it's by itself, right? I don't put a 2 here because it's with mercury. The Brinkelhoffs, those diatomics, only applies when they're all by themselves, not with anyone else. All right, then the next thing we have to do is balance. This one's a pretty easy one, right? 2 oxygens here, 1 oxygen here. If we put a 2 here, messes up with mercury. We put a 2 here. Now, all ionic compounds are solids, and all metals are solids except for mercury. Mercury is the only exception to the rule. If I had a colored periodic table, you could see mercury is a liquid and all Brinkelhoffs are gases except for bromine. So our only real exceptions, so I'm just going to write this down. All ionic compounds, solid. Brinkelhoffs, gases, except Br, which is a liquid. All metals, solid, except Hg, which is a liquid. So that should help us with our states. The covalent compounds, those ones are a little bit more difficult, but these should help us get most of our states down. Okay, so now we're going to try another one. So here's exactly what we did, and then we did our solids. Okay. Now I have to erase all these. Here's another one we've got. Electricity is passed through molten sodium chloride. Well, this one's actually pretty simple, right? Because you have Na, sodium chloride, Cl. This one you don't really need to look at because there's really only one option here, right? So this one is number 1 on here, which I know it's backwards when I show you. Binary compounds can decompose by heat or electricity. Binary just means 2. So NaCl, that would be a binary compound. So they can decompose by heat or electricity. So when we do that, we just separate it, Na plus Cl. Okay, so now I want you to complete this, whether you're watching this now or you're watching the recorded version of this. I want you to complete this, and then I want you to tell me what coefficient we end up with right here. So complete this whole thing. So step 1, classify. Check, did that. Step 2, write our products. Step 3, we have to balance our charges. Step 4, balance the reaction. So I'm seeing lots of them come through. Yeah, so again, tricky piece here was that Brinkelhoff. That is a 2. Again, only because it is by itself is it a 2, by itself. So because that is a 2, this is a 2. And then we have to do our states. All ionic compounds are solids. All metals, except for mercury, are solids. Brinkelhoffs are all gases, except for bromine. Okay, now I'm going to do the same thing with KF. So I know you can't. Here's the NaCl one. So let's try doing the same thing with KF. So if we have KF, binary compounds can decompose by heat or electricity. So it's going to come apart into K and F. Okay, I want to do the same thing. Finish this, but tell me what is the coefficient in front of KF. So do this whole problem, and then tell me what is the coefficient in front of KF. Yeah, it's almost the same problem that we just did, right? So when we do this, step 1, classify the reaction. Step 2, write our products. Step 3, balance our charges, including any possible Brinkelhoff. Then we have to put a 2 here to balance it. Solid, solid. Again, this will be a gas because all Brinkelhoffs are gases. Okay, let's see here. Let's see. Oh yeah, sorry, I forgot the 2 here when we did that. Yeah, thank you. Okay, so now let's try another one. So here's the rule. Let me just erase this. Metallic chlorates decompose when heated to metallic chloride and oxygen. So this is a metallic chlorate because this is a metal and this is a chlorate. See those polyatomic ions? They're never leaving you. Like I said, no matter what you do, they will keep coming all semester long. So you might as well just remember them now and save yourself hours of pain and agony. So you need to recognize that that is a chlorate. And then it says it decomposes. And again, this one is number 2 on the sheet. This is number 2 on the sheet. Decomposes when heated to a metallic chloride. So that just means a metal chloride and oxygen. So the metal we have is lithium, chloride, and oxygen. Right? Okay, got that. That's kind of our basic piece.
Could the metallic element be any metal, or at least in the general in this equation here?
Any metal.
Okay.
Yep, any metal in this case. Unless there's an exception, it can be any metal at all, unless it says except for, and there's no except fors. So any metal. So now the next part we have to do is we need to balance our charges. So we need to look at these charges here. And this is, again, great review for exam 1. Li is a +1, Cl is a -1. Well, nothing to do there. Oh, we've got a Brinkelhoff. We have to add a 2 here. The next step, balance the reaction, right? And so when you balance it, again, however you like to balance it, I see there's 2 oxygens here and 3 oxygens here. Common number between those is a 6. So if I multiply this one by 2 and this one by 3, I'll have 6 oxygens in both. And that messes with your chlorine. So you put a 2 and you're good. Okay, so now we have to do our states. Ionic compound, solid. Ionic compound, solid. Brinkelhoff, gas, right? And so this is what we mean. This is what you're going to be doing this entire chapter. And then after this, you use it for your next exam too. So we start doing math with these balanced chemical equations for your third exam. And we use that again for your fourth exam. So that's why, again, that elements and compounds module, so important because we use it the entire semester. Okay, so here it is neater. Much prettier now. And there we go. Okay, so let's try another one. So I'm going to give you a minute, and I'm going to let you try this one on your own, and then we're going to go over it. And then you can just type your answer in the chat, or you can, again, just write it down on your paper and then check it when we go over this. So I'll give you a minute, maybe 2 minutes, and we're going to go over this. Remember, step 1, classify it. Well, they're all decomposition because I told you. Step 2, get those products. Step 3, balance your charges. Step 4, balance your reaction, and then add your states. So try that, and then we're going to go over it in just a second. All right, I'm seeing a bunch of them come through now. And again, put this on your computer, on your paper. So metallic oxide, again, just a metal and oxygen and carbon dioxide. So this is our metal. This again, this is our carbonate. We have to know those polyatomic ions. When we do this, it separates into our metallic oxide. So that's our metal plus an oxide. Remember, oxide is just the element and the oxide together. And carbon dioxide, again, got to be able to name, got to know our nomenclature. And we need to check our charges. Well, magnesium's a +2, oxygen's a -2, so we're good. Then we have to balance our reaction. Well, nice, it's balanced, right? There's 1 magnesium on each side, 1 carbon on each side, and 3 oxygens on each side. But then we got to do our states. Ionic compounds, solid. Ionic compound, solid. CO2, this one we just know from our life that carbon dioxide is a gas, right? So sometimes we just use our knowledge of living, but we know that carbon dioxide is a gas.
Wouldn't MgCO3 be Mg parentheses CO3 end parentheses 2?
So great question. So magnesium is a +2. Carbonate's a -2. So therefore, there's just 1 magnesium and 1 carbonate needed. So their charges cancel.
Okay, never mind. I thought it was, never mind.
Yeah, great question though for your first exam, because that's exactly the kind of stuff that's on your first exam. And then we put all of our states in. And so your next quiz and your next exam is doing this. It's the entire quiz and it's the entire exam. And then again, for your third exam, we're going to start doing calculations with this. So again, sometimes we're faster at this and sometimes we're slower at this. It's okay. I try to always give you lots of time. And we're only going to do a couple of these, and then I'm going to throw all different ones at you and you're going to have to figure these out. So now let's look at
why you split it up like that again? Why the C is why is the C not with the Mg?
Why is it like this? Yeah, because it's this. So here's the rule. So when it says, so all that we saw was this piece right here. So then you look at this sheet, which hopefully everyone has pulled out. Here's the rule from the sheet. right? So I just typed it out. And so you realize that this is a metallic carbonate, because that's the metal and that's the carbonate. So then we look for the rule that talks about metallic carbonate, and it says it decomposes, that's our arrow, to a metallic oxide and carbon dioxide. Here's our metallic oxide, and here is our carbon dioxide. And that's how we know what these products are.
Oh,
Yeah, and so that's why these little rules are handy. Otherwise, you have no idea which one goes with which one. Okay, so let's look at single displacement. Now, single displacements are, again, pretty easy to see. But again, you're only going to be seeing this piece now, right? You're not going to be able to see this piece. So how do you recognize a single displacement reaction? You see one element all by itself, and then you see a compound. So your key is you see this element, and then you see a compound. That's how you're going to recognize that it's a single displacement reaction. And what's going to be happening, we look at what happens here. So remember, a good way to remember single displacement reactions is elements don't want to be by themselves. They want to be with other elements. They don't like to be alone. So again, I drew this kind of funny last time. We have a sad copper over here. Copper sees silver, gets to be with the nitrate. Copper's like, I really want to be in nitrate. So copper comes here and says, silver, get out. And then copper gets to be with nitrate, and now silver's left on its lonesome, right? And so we actually do this in lab. We actually make pure silver. I don't think you guys are going to get to do it at home, but maybe in 219 you'll get to do it. But this is a single displacement reaction. So here, we're going to be looking at the rules down here for single displacement. So here again is an example of a single displacement reaction and another example of a single displacement reaction. How can we tell? Element by itself, compound next to it. Element by itself, compound next to it. Remember, an element is one, compound is two or more elements. Again, great review for your exam. So if we look at this, what happens here, any element on its own, they all have charges of 0. All by itself, they all have charges of 0. They don't like to have 0 charges, right? If we look at this here, look at our aluminum, and from a 0, here it's a +3 and oxygen's a -2. Aluminum really likes to be +3. We're going to talk about why throughout this whole semester. If we look here, iron is a 0 here, and here it's a +2, oxygen's a -2, right? +2. And so the charges on these change, and they like charges. They don't like to be zeros. They don't like to be by themselves. Okay, so when we're looking at single displacement reaction, the question is, how can we figure out who is going to kick out who out of a reaction? Because sometimes we get reactions and sometimes we don't. So we use this thing called an activity series. And I think I put your activity series on, I have the old page, on that new reactions handout, but if not, I'll show you. This is a very complete activity series. And so how you read these activity series is, the higher an element is up here on the top, means it can kick out any element on the bottom. It can displace them. So what you do is you look at this, these guys are the sad ones down here. They can't kick anyone out. These ones can kick everybody out down up here. So the question is, will magnesium displace hydrogen? If magnesium is above hydrogen in the activity series, it can kick it out. So we look at the activity series. Here's magnesium. Here's hydrogen. So can magnesium displace hydrogen? Yes, it can. And we're going to actually be doing this one in lab. I looked at one of your labs. We actually get to do this one. So what happens here, so I'm going to draw this on this reaction so you can see. So again, here's magnesium all by itself. And then hydrogen, it's to be with chlorine. When we're doing single displacement reactions, positive can only kick out positive. Negative can only kick out negative. What do I mean by positive and negative? So cations are positive. Cations are positive, anions are negative, right? Magnesium wants to be positive. Hydrogen is a positive. So magnesium can kick out hydrogen. And then poor hydrogen is all by itself, and now magnesium gets to be with chlorine. That's an example of a single displacement. Okay, let's try the next one. Can aluminum displace hydrogen? So we have to look.
Yes.
Aluminum, hydrogen, can it? Yeah, right? Okay, next one. Can iron displace zinc? Here's iron,
No.
zinc. Can iron displace zinc? No, right? It can't. So if we had a reaction where iron was displacing zinc, you know what happens? Nothing. The answer is no reaction. Nothing happens. Okay. So let's look at a couple of these. So on your sheet, this is the activity series that I have for you, and then I'll give for you on quizzes just because it's easier. It's the exact same thing as this. So I'm just going to go back so you can see. It's just horizontal. See, here's like K, SR, NA over here, and like PT and AU are down there. See, PT and AU. Here's like K, right? So it's very similar. It's just horizontal. So this is like the top, and this is like the bottom. And you get to use this on your quiz and your exam. So what happened is somebody did a ton of experiments, like tons and tons of experiments, and then created this nice activity series for us. So we just need to be able to use this activity series. Okay. So here's the rule. Active elemental metals react with less active metal ions. Okay. So what does that mean? Whenever you see single displacement, your first thing should go in your brain is, I need to look at the activity series, right? So I always tell people, I actually wrote this on here. Sorry, if you can see it. It says single displacement and it says see activity series. Like I literally wrote it on there so you would remember, go look at the activity series. So if we look at this, we have magnesium. And then we have iron 3 oxide. Oh, let's see, practice for your exam again. This 3, right, is the charge on iron. Oxygen's -2. So now, our question is, magnesium is not happy. It's going to kick out one of the two. Which one is a magnesium going to try and kick out? Is it going to try and kick out iron, or is it going to try and kick out oxygen? Which one is magnesium going to try and kick out?
Iron. Because it's a cation?
Yeah, iron, because it's a cation, right? That's what I mean by positives can only kick out positives, negatives can only kick out negatives. Magnesium, right, is going to be a +2. Iron is a +3. So, or think of it this way, metals can only kick out metals, non-metals can only kick out non-metals, right? So magnesium, the question is, can magnesium kick out iron? So on your activity series, you're going to look at, is magnesium above iron? Because if magnesium is above iron, then a reaction will occur. Magnesium could kick it out. But if magnesium is not above iron, then nothing happens. So we look, here's our iron. Here's our magnesium. Our magnesium is above it. So oxygen's out of there. So that means that magnesium now gets to be with oxygen. And poor iron is all by itself. Okay, so now that's just our first step. Now we need to balance our charges. Now remember, the reason this 2 is here and this 3 is here is because we had to balance our charges here. We don't take the 2 and the 3 over. We do not do that. Remember, it is separate, right? Our reactants and our products are separate. They're 2 different pieces. We have to balance the charges individually. So in this case, we check +2, -2. We're good. Iron, any by itself, right? It's not a Brinkelhoff, so it's just Fe, right? It's not a Brinkelhoff, so we just leave it. Then our next step is to balance the reaction. And again, I'll balance this one the long way, but you do not have to balance this the long way. You feel free to balance this however you'd like. If you need to balance it the long way every single time, that's fine. Do this every single time. I try to leave you enough time on your quizzes and your exams. If you do balance a long way, you can do it. You have enough time. So I don't know, I'm just gonna do iron first. That was easy. But now oxygen, I have to multiply this by 3. Well, that messes up my magnesium. So I'm gonna multiply this by 3, and it's my magnesium. And again, if you don't need to balance it like this, you don't have to use the long way. Next step, states. All metals are solids. All ionic compounds are solids. All ionic compounds are solids. All metals. Actually, this one actually might be a liquid in this case, but it's okay because it's heated, but I would be fine if you said it was a solid. Okay, so now I'm gonna write this neater. Sorry, I can't erase this very well anymore. Solid. So again, this all started with just this piece. So there's a lot of steps you have to take. If you look on the back of your reaction, the back of your page, I gave you like 5 different steps to do every time you have to do one of these problems. Okay, so I'm going to give you a minute and you're going to try this one on your own. Actually, I'm going to give you literally 1 minute on this one because you shouldn't need more than that time. So try this and tell me what we get. Yeah, I'm seeing people like, well, this doesn't work, right? How do we know it doesn't work? So here's iron. Remember, iron, sad, doesn't want to be on its own. It wants to be with oxygen. So the question is, can iron kick out magnesium? So we're looking at iron needs to be above magnesium, but iron's below magnesium. So you know what happens? Nothing. Literally, your answer is no reaction. These are the best because you know why they're the best? You don't have to balance the reactions. You don't have to write any products. You just get to write nothing or no reaction, right? So we love them when there's no reaction. A lot less work for us. So you have to, number 1, check the activity series if it's single displacement. Otherwise, you're going to go through all this extra work that you don't need to do. Okay, so this again, this is straight from that handout that I gave you. And so here's our active elemental metals. So it's just a metal reacted with a less active metal. How do you know if it's less active? Activity series, right? You have to look at that activity series. Now this one, active elemental nonmetals react with less active nonmetals. There's not an activity series for the nonmetals, but here is your most active. Here's your least active. That one doesn't really even exist. So most, least. So this is like your own activity series on the periodic table. So we don't actually create an activity series. You just use the periodic table for this. Right? Just use your periodic table for this one. Periodic table. And then most metals will react with hydrogen ions from acids. Again, that's just going to be looking at the activity series. And then alkali metals below magnesium. Alkali metals, which again, great practice for exam 1. Alkali metals, group 1. Alkaline earth metals, group 2, below magnesium, will react with hydrogen with water to form a metal hydroxide and a hydrogen gas. So that means all of these. I'm just going to erase some of this. So this one refers to all of those. So you just need to read them kind of carefully. And so alkali metals and the alkaline earth metals below magnesium react with the hydrogen from water to form a metal hydroxide and a hydrogen gas, right? So if we have, let's just do Na plus water. Using this rule, it says that it will react with the hydrogen from water. So it's going to kick out this hydrogen to form a metal hydroxide. Metal. Oh, look at, there's that exam 1 stuff again. Hydroxide and hydrogen gas. Brinkelhoff. Okay. So if this was BE or MG, then in that case, yeah, nothing happens. It just, so if you had magnesium with, we'll say cold water, you can actually get it to react with warm water. What do you get? Nothing. You get magnesium sitting in water. It's not very entertaining, unless you heat it, but in cold water. And for example, this one right here, if you do like potassium, and actually this by the way is so reactive, it actually like lights on fire. It lights the water on fire. It's so reactive. Okay, so let's try this one. Let's do strontium plus water. So for this one, very similar. So it's going to make strontium hydroxide plus H2. I want to see if anyone can figure out my mistake. There's a mistake here. Besides, yes, it's not balanced yet. Actually, it is balanced. But I've got another mistake. What's the mistake?
On the SR, it's on the compound side, it's be SR parenthesis OH parenthesis 2.
2, right? Yes. So this is an important thing when we're doing this chapter or module, and for all the rest of them, you have to remember to balance the charges. Everything that we did for exam 1, you have to keep doing it every single time. Okay, so let's practice a couple more. So here's what we were talking about with our nonmetals, which I'll have to go back to the periodic table in just a second. So chlorine gas, Cl, plus sodium bromide. And at this point, we should all be able to go, oh, that's NaBr. You should have maybe look at your periodic table. I'm just going to do this one right here, just because I want you to see the periodic table on this one. So we're looking at this piece right here. So it said chlorine gas is bubbled through sodium bromide. So remember, +1, sodium's a +1. Here's bromine, it's a -1. So the question is, can this occur? Remember, this is like your own little personal activity series. The higher it is up, the more active it is. So the question is, remember, chlorine is very sad by itself. Can chlorine kick out sodium? By the way, Brinkelhoff, right? Because it's by itself. So can chlorine kick out sodium? Is that the right question? Anybody gonna catch it? It's okay. Remember, metals can only displace metals. Non-metals can only place non-metals. So the right question is, can chlorine kick out bromine? Because chlorine is a non-metal and bromine is a non-metal. Or think of it as pluses only replace pluses, right? Minuses can only replace minuses, right? Both chlorine and bromine are both minuses, right? So negatives can kick out negatives, positives can only kick out positives. So if chlorine is above bromine, then it can kick it out. It is above it, so it can happen. So bromine, sayonara, chlorine gets to be with Na now. And then poor bromine is left all on its own, right? So the question, remember, non-metal can only kick out a non-metal, right? Or negative can only kick out negative. If it's non-metals, you look at the periodic table. If it's metals, you look at the activity series. Then we have to balance it. Br is a Brinkelhoff. Bromine is -1, right, because it's in group 7. But bromine has to be a Brinkelhoff because it's the Br in Brinkelhoff, right? So it needs to be diatomic. Then we have to balance the reaction, which is what we did yesterday or last class. And so when we do that, trying to make this a little neater, put a 2 here. It's not letting me write on it now. There should be a 2 in front of the NaCl. My pen stopped working. And then we should be good. And then we still have to do the states, right? So now I'm going to go here to see this meter without a periodic table. So we balance it, states. Okay, now the next thing we need to talk about is aqueous. So we've done solids and we've done gases, but aqueous. So solution means dissolved in water. Dissolved in water is aqueous, right? So solutions mean dissolved in water, and dissolved in water means aqueous. So because this says solution, that means we're operating in water. Therefore, all of our ionic compounds are aqueous, not solid. So if you see solutions, now we're talking about aqueous. Okay, let's try another one. Or I gave you the answer here. So this one is liquid bromine is poured into a sodium chloride solution. So Br plus NaCl. So when we do this one, again, we're not looking if bromine can replace sodium because bromine's a nonmetal and sodium is a metal. Nonmetal can only replace nonmetal. Bromine, the question is, can bromine kick out chlorine? So the only way this can happen is if bromine is above chlorine. So let's look. I have to go back to our periodic table. Bromine, chlorine. Bromine is not above chlorine. So that means we don't need to do any more work. The answer is just no reaction and we're done. No reaction, right? Again, those are our favorites. Always make sure you check because you want it to say no reaction because then you don't have to do the rest of the problem. Otherwise, you're just doing extra work for no reason at all. All right, so our next one is here. Most metals react with hydrogen ions to form acids. Or from acids, I mean. And so you can just use the periodic table, the activity series for this, and there's that hydrogen. So you just use hydrogen. It's the same as we did with the very first one. So zinc metal reacts with hydrochloric acid. Oh, again, good exam review. What's hydrochloric acid? Type it in the chat or write it on your paper. Hydrochloric acid, hydrochloric acid, hydrochloric acid. Yes, HCl. So we have zinc plus HCl, right? Great review for our exam. So again, we're looking for so we're saying, can zinc kick out hydrogen? Not chlorine, because zinc's a metal, right? Chlorine's a non-metal, and it's not on our activity series. So if zinc is above, so we're saying, is zinc above hydrogen? So we look here, oh, zinc is above hydrogen. So zinc is above hydrogen. So hydrogen, you're out. Zinc gets to be with chlorine. So we've decided that these are our products, but now we need to balance the charges and fix our products before we balance our reactions. All right, so we're not even gonna look at our reactants anymore. We're only gonna look towards our products. And again, this is exactly what you did in exam 1. Perfect review for exam 1. We have to fix these. Okay, ZNCl, that looks good to me. Is there anything wrong with the ZNCl? Looks good? Should we just leave it? I'm seeing yes, right? Zinc is +2. Chlorine is -1. So it should be ZnCl2. And hydrogen is a Brinkelhoff. When it's by itself, it's a diatomic, right? Again, this is exactly what you did in exam 1. None of this is new. Okay, so our next step.
Balance.
Balance. Yeah, and so balance. And again, however you want to balance it, you can. This one's kind of an easy balance when we do this. And then we put in our states. All metals are solids. All acids are AQ. We sort of talked about this last chapter, but now we know all acids. To be an acid, it has to be dissolved in water, right? So it has to be dissolved in water to be an acid. And since we're in water, that makes this an AQ also because we're in a solution. And this will always be a gas. Okay, so now I'm going to write this all neater for you. It's coming neater. So there's a lot of different processes that we have to do for these. Okay, so now I want you to try this one all on your own, and then we'll go over it in just a minute. All right, see a lot of those? Yep, no reaction, right? So you can do a lot of work, right? It's easy. If you don't look at the activity series, you're gonna end up doing a lot of extra work. But since we looked at our activity series, we could see that copper is below hydrogen. So it is unable, it cannot kick it out. So if you put copper in HCl, do you know what you end up with? A piece of copper sitting in HCl. That's what you end up with. Nothing happens. If you put zinc in HCl, you see bubbles. And then the zinc ends up disappearing and the zinc goes away. And we're actually going to be doing that experiment next week or the week after. Okay, now here's the other one we talked about. We looked at this one a little bit about the alkali metals. So we did the sodium with water, right? So they alkali and alkaline below magnesium react with the hydrogen from the water to make the metal hydroxide and hydrogen gas. So when we do this, here's another way you can write it, just because it kind of makes it easier to figure this out. Let's see here. So when you do this, you can kind of think of it as the Na is kicking out this hydrogen. Sort of, that's kind of how you can think of it, if it helps you see it as a single displacement reaction. So if you rearrange your H2O to be HOH, you can kind of see what happens, because here's your Na and there's the H and it's kicking it out. So whichever way is easiest for you to see, if you just want to memorize or not memorize, use this or kind of rearrange it, whichever way. And it doesn't matter if you had H2 first or NaOH second. it doesn't matter. As long as you have your products and the products and your reactants, the order of them does not matter. What does matter and what is important is that it always goes positive, negative, right? When you're doing your ionic compounds, it always goes cation, anion. That is an important thing. So your positive always goes first. Okay, and since we did this one, balance it, put all of our states, remembering that water is really, so there's really 3 L's that we use. We use bromine as an L. We use mercury as an L and water as an L. It means it's pure and nothing else in it. If the only other time you would see L, if it said like molten, so molten like lava, like molten, liquid. So if it said like molten iron, that's like liquid iron. So then you would have an L, but it would have to say like molten. Just think like lava. It's actually a liquid. Okay, so those are our single displacement reactions. Now we're going to look at combustion reactions. And combustion reactions don't really necessarily fit in any of the others, but they're pretty basic. And so for a combustion reaction, there's 2 things you always have to have. You have to have oxygen and a flame, right? That's a combustion reaction. So just think of a candle, right? Or every time you light your stove, right? You have methane, that's what's coming out of your stove, and oxygen, and you light it, and it makes CO2 and water. And so on here, I have combustion, and my rule, do I have it here? I have it here. I'll talk about it in a second. So here is an element plus oxygen, fire, makes what we call an oxide. Element plus oxygen makes an oxide. You can see this, by the way. Do you see this could be classified as a different reaction also? What could we have classified these reactions as? Yeah, these are combination reactions, right? Or synthesis. So combustion doesn't really fall in one, it could fall in multiple. So if, for example, if we were in lab, we would do this one. I don't know if you get to do it on your own. It's quite fun. You could say that's a combustion reaction because it's burning, or you could say it's synthesis. Both of these would be correct. So as you can see here, the only rule you need to know about combustion is it makes an oxide compound of each element in the compound burned. Okay, so that means each element in the compound gets an O next to it in the products. So in this compound, we have C's and H's. C's and H's. So then we're going to make C's and an O, that's an oxide of carbon, and H and an O, an oxide of water. Now, which oxide is it going to make? The one you're used to seeing the most. CO2, carbon dioxide, water, right? So if you have C's and H's, it will always make CO2 and water every single time, no matter what the combination or what the numbers of C's and H's you have, it always makes CO2 and water because that's an oxide of carbon and an oxide of hydrogen. And you need, as your other reactant, oxygen. Think about when you have a candle. If you want to put a candle out, you just put the top on it. Candle goes out. The reason it goes out is because you took out oxygen. So in combustion reactions, the other reactant is always oxygen. Now balancing these is like a Herculean feat. They're kind of difficult. This is the hardest one to balance. I always say just memorize this one too, 25, 16, and 18. The key to balancing combustion reactions really is this number here in front of what we call the hydrocarbon, because this is a hydrogen and a carbon. It's either a 1 or a 2. So that's usually a 1 or a 2 in the front, and it kind of helps. Okay, so let's just look at one of these. So again, combustion again means reacting with oxygen, and it makes an oxide of each of these. So we have methane that burns in air. C's and H's makes an oxide of carbon, CO2, and an oxide of hydrogen, which is water. If you ever have C's and H's, you always make CO2 and water. And the pain in this one is balancing it, which I'll write this here. It's not that bad. They're just kind of annoying when you balance them. So 2, 2. And now methane is a gas. You wouldn't necessarily know that, so I wouldn't expect it, but just think of methane, propane, right? That's grills. Methane, propane, butane, those are all in grills, so those are gases. Oxygen, we know is the gas. Carbon dioxide, we know is the gas. And in this case, it's water is actually a gas. It's just going out as water vapor. Okay, so our last one will just be octane. And again, C's and H's, octane, that's the stuff we put in our gasoline. This is literally what's in gasoline is octane. It's always going to make every single time CO2 plus water, right? Always the other reactant is oxygen. C's and H's always make CO2 and water. And in balancing, remember I said, remember this one, 2, 25, 16, and 8? 2, 25, 16, and 8. Some people like to do it with fractions. That just makes your life so much harder. Don't do it with fractions. They're sort of difficult to balance. Gasoline is a liquid. Octane is a liquid. That's how we know. Oxygen gas, CO2 gas, water gas. Okay, so that's combustion. So we did a lot of those today.